Okay, we're going to continue on here. We're in chapter 7. We started talking about equations and how to balance equations. So remember, when we do look at an equation, there's two parts to it. There's the reactants, which are your starting material in a chemical reaction. They go and form our products, which obviously are what is formed as a result of the chemical reaction. Remember that in a chemical reaction, really the only thing that we're doing is breaking bonds and making bonds. So we're going to break all the bonds on the reactant side, and then all the elements are going to reassemble on the product side into new compounds and new molecules. It only involves electrons, so we do have conservation of the elements, and that's because we're not playing with anything in the nucleus, so we're definitely not playing with any protons in a chemical reaction. So because it's only about electrons, the elements stay the same. As we talked about a number of times, it is the protons that determine what element you're dealing with. So because we're not touching any of that, we always have the same number of elements. That's really important for the balancing of the equations. When we balance the equations, we do need to end up with the same number of elements on both sides of the arrow. Um, so if we have an equation, the first thing that we do is we want to make sure if we happen to have things in words, we definitely, as we talked about, want to make sure that you get all the correct formulas down first before you even think about balancing the equation. So if you don't have the correct formulas on the reactant side or the product side of the equation or the arrow, I'm trying to balance. Once you do have all the correct formulas, we talked about sort of making a table, which is sort of helpful. And again, I like table reactor side, product side, just that are there, and just kind of add up what is present. So here, 1A on the right, our left, and 2 on the right, 1B on the left, and 2Bs on the right. Just gives you an idea maybe where to start with. Remember that when we are balancing equations, the only thing that we can change are the coefficients. So those are the only things, the numbers that come in front are the only things that can change. So in this case, we obviously could put a 2 here and a 2 there, and that's going to give me now 2A and 2B. Remember, when you do put a coefficient, it does go for everything that is behind it. So you do need to kind of multiply through everything behind it. When it's all said and done, we need to have a couple things met when we balance the equation. All the coefficients, again, has to be whole numbers. So we can't have decimals or fractions or anything like that when we're all done. And they do need to be, as we talked about, the simplest set of whole numbers. So again, a reminder that if we did have a balanced equation like we talked about last time, where maybe these are the coefficients you ended up with, again, you can go through each of these coefficients really and divide by 2 and reduce it down to A plus 2B goes to 3C. And this would be the properly balanced equation. Again, sometimes it does happen as people see sort of larger numbers to balance it, and it's absolutely balanced with the larger numbers. But if you can go through all your coefficients and divide by a common number and still end up with whole numbers for everybody, then you should do that and kind of reduce it down to the simplest whole number. Other things that we saw, right? We had something like this. And a reminder that if you do have a 3 on the outside, you do have to kind of multiply that in. I don't think there was a 2 there, actually. Put a little extra 2 for free. We'll get rid of that. Get rid of it there. Again, you do have to multiply in with those parentheses. So that would give us 3 oxygens and 3 hydrogens multiplying in. A reminder as well, if you then put a coefficient like we did in that example, you also need to multiply everybody by that coefficient. So like we did in there, that would go for everybody behind it. And that would give us, again, 2 borons, 6 total oxygens, and 6 total hydrogens as well. So you kind of have to multiply in and then multiply out if you do have something with parentheses. Any questions on any of that there? All right, take a look at maybe a couple more here. All right, I want you to give it a go here and balance this up. See what you come up with here. Okay, okay, let's take a look and see how you're doing. Once again, we're going to make a table here, a little reactant product side. Here we have nitrogen, hydrogen, and oxygen happening. And on the left-hand side, we have one nitrogen. Right-hand side, we got one nitrogen. Left-hand side, we have three hydrogens. I'm sorry, left-hand side, we have three hydrogens. Right-hand side, we have two hydrogens. Left-hand side, we have two oxygens. And right-hand side there, we have two oxygens. Yeah. So really, at this point, the nitrogens are good. The oxygens are good. It is really the hydrogens that are not so good. We have three on one side and two on the other. So we need a kind of a common number between those two. So if we just multiply 3 by 2, that is 6. So we basically need to get our hydrogens to 6 on each side. So to get our hydrogen on the left-hand side to 6, we do need to put a 2 there. And in this case, we actually need to also put a number on the right-hand side to get our hydrogen to 6. We would have to put a 3 here. At that point, that now, a reminder, the 2 is going to go to everybody. So that's going to give us now 2 nitrogens. 2 times 3 there is 6 hydrogens and 2 oxygens still. We still have 1 nitrogen. Hydrogen, again, 3 times 2 is 6. And for the oxygens, we do have 1 here. And we do have to multiply this by 3, which would give us 3 there. So now that's going to give me 4 total at this point. Now we fixed the hydrogen, but kind of screwed up everybody else, which is very common here. So once again, we want to kind of think about what's maybe the easiest thing to fix. And here, nitrogen should be pretty simple to fix. We just need to put a 2 on the right-hand side there in front of the nitrogen. That, again, is going to go for everybody behind it. And that'll give me 2 nitrogens. We still have 3 times 2 over here for 6 hydrogens. Now, in terms of the oxygen, we have 2 times 1 in the first thing here, which gives us 2. And we still have 3 times 1 over here, which gives us 3. And now we have 5 oxygens, right? So clearly at this point, we have everything balanced except for oxygen. We clearly do not want to start removing numbers because that just seems like we're going backwards. So really at this point, we really only have one location where we could put a number, right? And in this case, we need that number on the left-hand side to basically become a 5 to match the 5 oxygens we have on the other side. So in this particular case, one of the things that you can do is you can use something like a fraction and use something like 5 divided by 2. And if I do that, I will now end up with 2 nitrogens on the left. 2 times 3 is 6 hydrogens. And when I take 5 halves times 2, the 2's cancel, and we end up with 5. And now I have 5 oxygens there on the left-hand side. And technically speaking, my equation is balanced. Is it properly balanced, though? It is not, because I have a fraction, right? So this illustrates the point that you absolutely can use a fraction to balance the equation. And sometimes this happens when you have something like oxygen in its molecular form on one side and a couple things on the other side. But you cannot leave it as a fraction. So to clear the fraction, we have to multiply not just the fraction, but everybody by the denominator, the number on the bottom, basically. So if I multiply this entire equation by 2, which is my denominator over here, I'm going to get 4NH3 plus 5O2 goes to 4NO and 6H2O. And if I did not screw up, we actually should still be balanced. And we now should have actually a whole number. So let's take a look. On the left-hand side, we got 4 nitrogens. 4 times 3 is 12 hydrogens. 5 times 2 is 10 oxygens. On the right-hand side, we got 4 nitrogens. 6 times 2 is 12 hydrogens. We have 4 oxygens there and 6 oxygens there. 6 plus 4 is 10. And we are now properly balanced. So sometimes you may need to use a fraction to balance an equation. How do you know what fraction to choose? The recipe for the fraction is pretty simple. When you look back at what we had there, we need to put a number there. And if we just look back at what we had for the oxygens, on the right-hand side we had 5. On the left-hand side, I believe we had 2 in this case. So when you're going to choose the fraction, you put the number you need up on top. So I need this guy to be at 5, so the number you need goes up on top. And the bottom number should always match the subscript here. So the bottom number should always match whatever that subscript is. Then you will always pick the right fraction in that case. If you know what number you need, that goes up on top. Number on the bottom should always match the subscript, and then you will have the correct fraction that will balance out your equation. Any questions on that there? So again, sometimes very common, especially like I said, when you have kind of O2 or maybe N2 and those elements and different things on the other side. So if you get to a point where you're like, can't really make a 2 into like a odd number like a 5, think about a fraction is a good way to perhaps do that. Again, if you could see the bigger numbers like 4, 5, 4, and 6, you could just roll out those numbers, and again, you'd be in good shape as well. Any questions on that there? All right. Take a look at a couple other examples here. Now, when we look at this example here, there are a couple of things that are in this type of equation that you may want to take into account when you're going to balance it to actually make it easier on yourself. So one of the things that this equation has for sure is if you look on both sides, you will actually see some polyatomic ions. So you got some carbonate here, and you got some carbonate over here. You also have, in this particular example, another polyatomic ion on both sides. You got sulfate there, and you got some sulfate over there. So in this case, we actually have a couple of polyatomic ions on each side. And my recommendation is if you come across an equation where you have some polyatomic ions that are the same polyatomic ions on opposite sides of the arrow, it is oftentimes much easier to keep them together rather than trying to do it element by element like we've been doing. So kind of keep them together and just balance the polyatomic ions as like units rather than kind of going individual elements. You can definitely do like we did before with individual elements. There's just going to be a lot more multiplying in and multiplying out and stuff like that. But it's oftentimes a lot easier. So how would I approach this? Well, I would definitely look over here and go, okay, I got 2 carbonates over here. I got 1 carbonate over here. And over here, when I look at the sulfate, I got 1 sulfate over there. And I have 2 sulfates over there. And what I would do in this case is, honestly, you could choose either one to start with. One might work better than another, but you could choose either polyatomic ion. So I'm just going to say in this case, I'm going to choose carbonate to balance. So I'm going to focus in on my carbonates here on both sides. And when I look on the left-hand side, I have 2 carbonates. When I look on the right-hand side, I only have 1. So to fix the carbonate on the right, all I have to do is put a 2 in front of it. That now will give me 2 of those carbonates. But when I put the 2 in front of the carbonate, there's also another element there, and that is sodium, right? And by putting the 2 in front of sodium, I now have how many sodiums? I now have 4 sodiums. And by the way, this tells you where you should go next. So I now need to fix sodium that has 4 on the right, and if I look at my sodium on the left, it has 2, right? So I could fix the sodium on the left by putting a 2. I now have 4 sodiums on the left. That 2 also affects my sulfate, right? I now don't have 1 sulfate, I will have 2, yeah? Which if I look to the right-hand side, how many sulfates do I have? I have two. I'm good. I'm done. I'm balanced. Yes. So it's much, much quicker. It's much, much easier and probably less room for error if you have polyatomic ions on both sides of the arrow to just balance those guys. And what will happen is what we just saw here. By fixing the sodium, it will actually fix the sulfate and things will just fall into place. So it's sometimes a lot easier to keep those guys together. Mind you, you can only do this if you have polyatomic ions on both sides. So if you have equations like we had previously where there really wasn't polyatomic ions on both sides, you can't do it. You have to have the same polyatomic ion on both sides in order, obviously, to do this method. But it's a much quicker way and much easier way of balancing those equations without going element by element and having to do, like I said, a lot more kind of multiplying in and multiplying out and, a lot more individual sort of calculations. Any questions on that? All right, so why don't you try some here, balance up these equations, see what you come up with. Okay, let's take a look. So again, when I look at the first one here, I definitely see some polyatomic ions on each side. We got some nitrate, which is obviously, again, the same on each side. We also got some sulfate here, which is the same on each side. And once again, when I see that, I'm going to kind of take the approach of just kind of keeping those together. And I want to just kind of balance them as units rather than going element by element. Again, should just make it a little bit easier. As I mentioned before, you really could start with either polyatomic ion. And in some cases, one will work better than the other. But in this case, I'm going to start with the sulfate. And the reason I'm starting with the sulfate is just looking at the nitrate, I got 2 on this side and 3 on that side. And when I look at the sulfate, I got 3 on this side and 1 on that side. Just like before, it just seems much easier that I could balance the sulfate by just putting one number on. If I wanted to balance the nitrate here, I would have to put numbers on both sides, right? So it's a little bit more complicated. So just to kind of keep it a much simpler approach, I'm going to start with the sulfate. But like I said, if you wanted to start with the nitrate, it would work out the same as well. It just might be a little bit more numbers that you have to kind of start with. So starting with the sulfate, once again, we just want to keep it simple. I got 3 on this side, 1 on that side. So much easy to balance it is I just need to put a 3 in front of this. This will now again give me 3 sulfates. And when I do put that 3 in front, the other element that is there is really where you should go next. So I'm going to now look at the calcium, and I put 3 calciums there. I'm going to go over to the calcium on this side. I only have 1. So again, I could fix that easily by putting a 3 to fix the calcium. That now gives me 3 calciums. When I put that 3 for the calcium, it also goes for the nitrate here, right? So now I have not 2 nitrates, but 3 times 2 is 6. That's where I should go next. So I go to the other side to fix my nitrate. I'm going to put a 2 in front of it because I already have 3. And that's going to give me 6 nitrate. It will also give me 2 iron, which is perfect because that's exactly what I need on that side. And now I am done balancing this crazy looking equation, right? And again, if you kind of go element by element, you're definitely going to have a lot more kind of multiplying in and stuff you could be done. Might take a little bit longer. Any questions on that? And again, in this method, like I chose the sulfate at the beginning, where you go after you do the first one is whatever element's attached to. Then you go to the other side, fix that element. Then whatever element that's attached to, you go to that one, and you kind of keep going back and forth, and usually will end up okay. We take a look at the next one there. There you go. I feel like I lost some of my polyatomic ion there. We do have sulfate here. We do have sulfate here. We also have another polyatomic ion. We got phosphate and phosphate here. So once again, I'm going to take this approach, and if it helps you, you could count up how much of each of those polyatomic ions you have on each side. So clearly I got 1 sulfate there, 1 phosphate, 2 phosphates, and 1 sulfate. So in choosing where to start, this one's pretty simple because the sulfate's already balanced, right? So there's one sulfate on each side, so I'm not going to start there. So that means I'm going to start with the phosphate. I have one phosphate here and two here. So again, to balance the phosphate, I'm going to need to put a 2 in front of the phosphate. That's going to now give me 2 phosphates to match the one over here. Now, because the phosphate on the left is hooked up to the silver, that now gives me 2 times 3, which is 6 silver. And that's exactly where I should go next. So because I put that 2 in front of the silver, I'm going to go to the other side. And I see silver has 2. So to fix that, I put a 3. 3 times 2 is 6 silver. The 3 also goes for the sulfate. So now instead of 1 sulfate, I have 3. And that's where I should go next. I can go back to the other side. I have 1 sulfate. I'm going to put a 3 in front of it. Going to give me now 3 sulfates and 3 coppers, which is good as well because I do need 3 coppers on the other side. And now I am balanced. So again, just kind of keeping those things together is a much easier way to do these a little bit more complicated sort of looking equations with the polyatomic ions. And again, you just kind of start with 1, and whatever that's attached to, that's where you should go next. And whatever that's attached to, that's where you should go next until everything sort of falls into place. Any questions on that there? Okay. Last one here. I'm going to go back to the table method because there's no polyatomic ions there. So, yeah. Are you talking about this 2 here? Yeah. It's because I have put a 2 in front. And remember, when you put the coefficient in front, I'll go up on top. It goes for everything behind it. So because there's technically 1 phosphate here originally, now that'll be 2 times 1 phosphate will give us 2 totals. Yeah. Other questions? Okay, so again, like I said, no polyatomic ions, so we're just going to go table on this one. Again, we're going to have reactants, products, carbon, hydrogen, oxygen. On the left-hand side, 4 carbons. Right-hand side, 1. 10 hydrogens on the left. 2 hydrogens on the right. 2 oxygens on the left. We have 2 oxygens there plus 1 more there. That gives us a grand total of 3. At this point, once again, nothing balanced. So the easiest thing, in my opinion, to balance is carbon, right? So to balance carbon, all I have to do is put a 4 there in front of it. That's going to give me 4 carbons, 2 hydrogens. I now have 4 times 2, 8 oxygens there, plus my 1 over there, which gives me 9 oxygens in this case. Again, I'm going to go with what looks easiest to balance. Once again, hydrogen to me looks easiest to balance. The reason is what we talked about last time. When I look at oxygen, it's in a lot of things, right? Oxygen is kind of everywhere. But hydrogen's only in one thing on each side. We only see hydrogen there and there. So that's going to make it much easier to balance. So to balance the hydrogen, I got 10 on the left, 2 on the right. That's going to require me a 5 there to go in front of my hydrogen. That's going to give me 5 times 2, which is 10 hydrogen. I still have my 4 carbon. Now in terms of oxygen, I still have my 8 in the first one. But by putting the 5 in this one, I now end up with 5 there. And if we add 8 and 5, that is 13. Yeah. At this point, the only thing that is not balanced is oxygen. All of our oxygens on this side have numbers, so we definitely don't want to change those numbers. So we got to work with this number right here, right? This guy. So we need to turn our 2 into a 13. This is, again, a perfect spot to use a fraction, right? So once again, to pick the perfect fraction, the number that goes on top is the number I need over there, right? So on the left-hand side, what number do I need over there? It needs to be a 13, right? It's got to be there. That's going to go on top. On the bottom is going to match that number right there, the subscript, which means it's a 2. And now I have picked the correct fraction here. That's going to give me on the left-hand side 4 carbons, 10 hydrogens, And once again, when you take 13 times 2, that's going to get rid of it, and we're going to end up with 13 oxygens. It is technically balanced at this point. Can I leave it like that? I cannot. So once again, we do need to clear the fraction. So we're going to multiply everybody here by 2. And again, that is the denominator to clear it. And if I do that, that will give me 2C4H10 plus 13O2. Go underneath my table here. 8CO2 and 10H2O, hopefully there. And at this point, we now should be balanced. If we look on the left, we have 8 carbons here. We have 8 carbons here. We have 2 times 10, which is 20 hydrogens. 10 times 2, which is 20 hydrogens. 13 times 2 is a lot, but I think that's 26 if you multiply it. And on the other side, we got 16 oxygens in the first one. We got 16 in this one. And we have 10 in this one, which gives you 26 oxygens when it's all said and done. And we will be balanced at that point. Any questions on balancing equations? Okay. So again, non-polyatomic ion, make yourself a table and kind of work through the table. Polyatomic ions in there, keep them together, balance them as units. And again, just be on the lookout if you get to the end and you need to kind of turn a even number into an odd number. Probably a fraction is, a pretty good idea. Any questions on that there? Yeah. All right, the next thing we're going to talk about is types of reactions. And when we talk about types of reactions, there really is 2 big categories of reactions. And you could actually classify a reaction in several different ways depending on what you're looking at. One big category of reactions are what are known as double displacement reactions. And as we will talk about, double displacement reactions is the only reaction where you will essentially have 2 ionic compounds. And always when you have 2 ionic compounds, the exact reaction always occurs, which is these 2 guys switch partners. So they basically just switch partners. And on the other side, you form 2 new ionic compounds. And as we'll talk about, there are other ways that you can classify double displacement more specifically. Sometimes those guys on the other side will form a solid, which is known as a precipitation reaction. And sometimes they may form water, which is very common what happens in an acid-base reaction. The other sort of big category of reactions is redox reactions. And redox reactions involve electrons being transferred. And really over here, when we do double displacement reactions, 1 of 2 things typically form. A solid or water is formed. And the reason these 3 things are really important is these are basically the 3 main reasons why a chemical reaction will take place. So if you look at a chemical reaction, one of these 3 things are happening. Either you're going to make a solid, you made water, or you had some electrons being transferred. And under the redox sort of category, there's more specific ways of classifying those reactions. And those are things like synthesis reactions, decomposition reactions, single replacement reactions. So let's start with oxidation and reduction. And when we talk about oxidation and reduction, these 2 words always happen together, or these 2 things always happen together. Oxidation means that somebody will lose electrons, and reduction means somebody will gain electrons. And sometimes people remember this as Leo the lion goes grr, loss of electrons, oxidation, gaining of electrons, reduction. Nowadays, people are fond of the oil rig. Oxidizing is losing, reducing is gaining. You could put Leo the lion on the oil rig and you don't have to choose. He'll go grr, and you can just do both together if you like. So what happens in this case is in a redox reaction, something gets oxidized, something gets reduced. When somebody gets oxidized and you lose electrons, you typically become more positive, right? Because you've lost electrons and you now have more protons, which are positive, than electrons, and you become more positive. When somebody gains electrons, you become more negative. So if you could figure out, for example, the charge on these elements on each side of the arrow, you could actually figure out really simply what is being oxidized and what is being reduced by just following a basic number line. So if you got 0 in the middle, positive numbers are to the right, negative numbers are to the left. So if you look at an element on the left-hand side of the arrow and the same element on the right-hand side of the arrow, and you look at its charge, or its really oxidation number, and you see that it is moving in the positive direction on this number line, that thing is going through oxidation. If you look at the charge or oxidation state of an element on both sides of the arrow, and it is moving in this direction, becoming more negative, that thing is going through reduction. So for example, if I take sodium metal here and react it with a little bit of chlorine gas, make a little sodium chloride over here, do a little balancing since we're in chemistry class. There we go. Now, we can look at this and basically determine what is happening to each of these elements by looking at really what is known as the oxidation state, but we'll call it the charge in this case. One thing you hopefully know or might remember is if you have any element that is by itself, not combined with anybody else, so anybody from the periodic table just by itself, they do not have charges. So remember, things only get charges when they hook up in like an ionic compound, right? Metals and nonmetals, that's where we get those charges that develop. So when we look at the sodium on the left, sitting there, it has no charge, basically. And the chlorine, that is one of those diatomic molecules or elements, and that is naturally how it comes. And that also has really a charge of 0 or oxidation number of 0. But when sodium and chlorine come together, that is a metal and a nonmetal. As we talked a lot about, that makes an ionic compound, right? And when you have an ionic compound, you have a transfer of electrons. And the sodium over here on the right is actually the +1 charge, and the chlorine on the right is the -1 charge. So if we want to know in this sort of reaction who is being oxidized and who is being reduced, we could use that little number line to help us. And if we look at the sodium to start with, it is starting at 0. So if we take a look at the sodium, it's starting like at 0. And on the right-hand side, the sodium is ending at +1, which means it is moving in this direction, right, towards the positive numbers. And if somebody moves in the positive direction, it is becoming oxidized. It's going through oxidation. So here the sodium is going through oxidation. By the way, if you are able to successfully identify which one is going to be oxidized or which one is being reduced, the opposite thing is happening to the other thing because they always happen together. So if you could just figure out half of it, you know by default, this guy is going through reduction. We could still use our number line to figure that out. If we look at the chlorine on the left-hand side, it is 0. And on the right-hand side, my chlorine is -1, which means it's moving in the negative direction, which tells us it is being reduced. So this is actually a redox reaction that is occurring. We are getting a transfer of those electrons over to the chlorine here to make our sodium chloride. And that is really the basis here of a redox reaction. Now, by the way, you probably don't even need the number line in this particular situation because when we have an ionic compound, which is made up of a metal and a nonmetal, which one should always lose electrons? Should the metal or the nonmetal lose electrons? Which one becomes positive? The metal, right? And you only become positive when you lose electrons. So when you have an ionic compound, the metal should always be the one that's being oxidized because it should always be the one giving away its electron. For all those trends we talked about, right? They don't want to hang on to their electrons, so they're just going to give away their electrons. So they should typically always be the one that gets oxidized when they're hooking up with a non-metal. And non-metals have all those trends where they accept the electrons. And that means that the non-metal should always be the one being reduced in a situation like this. When you form an ionic compound, metal gets oxidized, non-metal gets reduced. Ultimately, what is happening here is that transfer of electrons, which is one of the three reasons why a reaction takes place. So really, this reaction is taking place to allow those electrons to be transferred, and that's why this reaction actually does take place. Any questions on that there? All right, let's take. Okay, we're going to continue on here. So we're talking about ways to classify reactions. As we'll see, there are many ways you could classify it, but really there's these two main sort of categories of types of reactions. And underneath those big sort of umbrellas of types of reactions, there's kind of more specific ways you could classify reactions that we'll talk about. So this is what we just basically went over. Again, whenever you have basically an ionic compound that has been formed, the metal part of it should always be the one that gets oxidized. It should always be the one that's losing electrons. And the non-metal should always be the one that is gaining electrons and being reduced. And really, that is really what's powering sort of this reaction to take place, is that transfer of electrons that always occurs in a redox reaction, whether or not you call it a redox reaction or not, or you classify it as a synthesis reaction or a decomposition reaction. That is ultimately what is really happening in those reactions, is there's some type of transfer of electrons that are basically occurring. Here's another example of it. Again, we have magnesium by itself. It has, when it's all by itself, that is the natural way that oxygen comes, which also has no charge. Once again, here we have a metal and a non-metal, like we talked about with naming, that and bonding. That's going to give us an ionic compound. When those two come together, that is when they have charges. The magnesium, which is group number 2, will have our +2 charge. Oxygen, which is group number 6, will have our -2 charge. So again, if you were curious what's being oxidized and what is being reduced, we could just simply follow, like I talked about a second ago. The magnesium here is starting at 0 on the left. On the right-hand side, the magnesium is ending at +2. It's moving in the direction as we would expect, because magnesium is the metal, right? So we would expect this. By the way, again, by default, that means that this one over here, the oxygen, will be going through reduction. And once again, you could do the same thing if you really wanted to. Oxygen starting at 0 on the left-hand side. It's ending at -2. It's becoming more negative. The only way it can become more negative is you have to gain electrons, right? Because electrons are negatively charged. So as you gain electrons, you become more negative, and it is going through reduction. Once again, not even necessary, the number line there, just simply knowing that's a metal, that's going to get oxidized. That's a non-metal, it's going to get reduced. The guy on the left there is going to gain electrons, and the oxygen is going to, the oxygen is going to gain electrons. The magnesium is going to send the electrons over to the oxygen in this case. Once again, a transfer of electrons is what is happening in this reaction. Later on, we'll talk more about oxidation and reduction when we get to organic chemistry. And in organic chemistry, we oftentimes don't look at charges, but we look at hydrogen and oxygen. So there are two other definitions that we definitely will see a little bit later on as we get into organic. Oxidation can also be when somebody gains oxygen as you go from reactants to products. So if you look at some element on the left-hand side to the right-hand side, and it's kind of gained oxygen, that means it also went through oxidation. Or it loses H2, or hydrogen, as it goes from reactants to products. That's another definition of oxidation. Reduction is basically the opposite. If somebody loses oxygen as it goes from reactants to products, it is being reduced. And if it gains hydrogen, it is being reduced as well as we go through here. The reason we look at hydrogen and oxygen when we get into things like organic chemistry is there's not a lot of metals, there's not a lot of ionic compounds. It's all covalent compounds sharing of electrons. So we don't get the transfer of electrons like we do with ionic compounds. So when you're dealing with something like organic, as we will see later on, you have to kind of look at the hydrogen and oxygen being gained or lost as an example of that. So here, for example, we could see the sulfur gained some oxygen as it went from left to right there, so it is being oxidized. We also see that the copper in the second one lost oxygen as it went from left to right, and it is being reduced. Because that actually is a metal, the charge on the copper here is +2 because that's an ionic compound and the oxygen is -2. The charge of the copper on the right-hand side is 0. So if you look at the little number line thing by looking at the charge of the metal, in this case, it's starting at +2, which would be over here, and ending at 0. It's actually moving towards the negative side here, which tells you it is being reduced. And that is, again, the same definition we get here because it is losing oxygen as it goes from left to right. So later on in organic, we will see these other definitions of oxidation and reduction as the source of whether or not it's being oxidized or reduced. But for now, we just kind of look at charges. And really for now, if you understand the metal loses electrons, non-metal gains electrons in an ionic compound, you should be pretty sufficient. So as I mentioned, there really is just 3 reasons why reactions take place. And these are really the 3 reasons that they take place. As I mentioned earlier, you can pretty much boil down any reaction, and one of these 3 things are pretty much going to be happening, and that's why it's happening. The solid and water being formed, as I mentioned before, those are the situations that fall under the double displacement situation reactions. And the transfer of electron is the redox reactions that we've been talking about. And again, that pretty much accounts for all reactions that take place. And you can boil it down, like I said, to one of those 3 things should probably be happening. Solid being formed, water being formed, or a transfer of electrons. So let's talk about more specific ways to classify reactions. And the first type of reaction is a synthesis or combination reaction. This falls under the redox category. So this is really under the big umbrella of oxidation and reduction reactions. The simplest way to explain a synthesis or combination reaction is 2 things make 1 thing. Not super complicated there. If you got 2 things that make 1 thing, it definitely is going to be a synthesis or combination reaction. We look at water formation. 2 things make 1 thing. Classic synthesis reaction. 2 things here making a sodium chloride make 1 thing is a synthesis or combination reaction. What is happening in each of these reactions? Well, we've already talked about this one here. Our sodium is getting oxidized and our chlorine is getting reduced, which means our sodium is sending electrons over. You may not see it in the top one, but the same thing is actually happening in the top one. The hydrogen here is 0. The oxygen here is 0. The hydrogen in water is +1. Oxygen is -2. So in this particular case, the hydrogen is going from 0 to +1, becoming more positive. The hydrogen here is getting oxidized. The oxygen is going from 0 on the left-hand side to -2 on the right, becoming more negative. It is getting reduced. So what is actually happening here is we're sending some electrons over, basically, from the hydrogen to the oxygen. And that transfer of electrons is really what's taking place here. Even though we call it a synthesis or combination reaction, what ultimately has happened here is a redox reaction where we are transferring those electrons. Any questions on that there? So that's kind of what you want to look for. 2 things, 1 thing, definitely synthesis or combination. The next type of reaction is a decomposition reaction. And honestly, this is also a redox reaction. So this also falls under that redox category. You could think of a decomposition reaction as pretty much the opposite of a synthesis reaction. So in a synthesis reaction, you put it together. In a decomposition reaction, you break it apart. So you start with one thing and you make multiple things. Right? So kind of the direct opposite there. If you ran an electrical current over water, it would break apart through electrolysis. One thing makes two things on the right-hand side there. This is a decomposition reaction. Also here, mercury 2 oxide. This will, one thing makes two things. Again, decomposition reaction. Same thing is happening here. There's actually a transfer of electrons happening. If you look at the mercury 2, that's +2 and -2, as that's an ionic compound. This again is the natural way those guys come, so they both have zeros. So again, if we just look at one of those things, like the mercury, mercury is starting at +2 on the left-hand side, ending at 0. The mercury here is getting reduced. It is the oxygen here that is getting oxidized in this case. It is going from -2, which would be over here, to 0. So that is the oxygen on that side that is actually getting oxidized in this case. So once again, there's a transfer of electrons from the oxygen to the mercury in this case. And again, that ultimately is what is happening in this reaction. Same thing with the water, basically. Any questions on that one there? So to recognize this one thing on the left, multiple things on the right, going to be a decomposition reaction. If you had carbonic acid, plop, plop, fizz, fizz, will break apart into water and CO2. Again, one thing makes two things, going to be a decomposition sort of reaction occurring. The next type of reaction is a single replacement reaction. And in a single replacement reaction, this is still under the category of a redox reaction. So there's still electrons being transferred. So in a single replacement reaction, you have this setup. And this is the only reaction that has this setup. You will have either a metal or it could be a nonmetal. And it'll be by itself with no charge, and you will have an ionic compound. And if this guy was a metal, it will come in and kick out the positive guy of that ionic compound. And that is because although the metal on the left-hand side does not have a charge, the one thing we know about metals is when it does get a charge, what type of charge should it have? Positive. So it's going to come in and kick out the guy with the same charge because it will not want to hook up with the guy with the same charge because that's two positive things and they're not going to want to be together, right? So it's going to kick out the positive guy there and it's going to make a brand new ionic compound where the metal will now have a charge and hook up with that negative guy. And the guy it kicks out will actually just pop off in this kind of natural form by itself, uncombined. And really, in order for this reaction to take place, whatever is coming in needs to be more reactive than what it replaces. So if this A is more reactive than B, this reaction will take place. If A is less reactive than B, it will not take place. So if you take something like what we see up here, this is zinc by itself. This is hydrochloric acid, which is basically an ionic compound. This zinc is going to come in and kick out the hydrogen, which is the positive guy. The result of that is hydrogen will come out by itself the way it naturally comes out, which is hydrogen gas. You'll see bubbles form. The zinc metal will start to disappear. You get a bunch of bubbles start to bubbling through your test tube or wherever you did this. And you will form a new ionic compound where the zinc will now gain a charge of +2, and the chloride will still be -1 in this case. This is a single replacement reaction. There is still electrons being transferred in this case. And just to show you again that you still have those electrons being transferred, if you look at the zinc on the left, it's 0. Zinc on the right is +2. It is going through oxidation like we would expect since it's the metal. The hydrogen on the left is actually +1. And on the right, it is 0, becoming more negative, is going through reduction. So it's actually the zinc that is losing electrons, and it is the hydrogen is going to pick those up in this reaction. Now, if you did this exact same reaction, but you swapped out the zinc for copper, you're going to get no reaction occur. And that's because copper is less reactive than hydrogen. It will not be able to really kick it out. There is, in most books or places, what is sometimes referred to as an activity series. It's basically a bunch of elements listed. Hydrogen is somewhere on the list. And basically, if you ever see an activity series, the way it works is this. Anything that is higher on the list will be more than happy to replace anybody lower on the list. So those reactions will take place. But anything lower on the list will not replace anybody higher on the list. So if you look at an activity series, you would see zinc higher than hydrogen, and that will replace hydrogen. And you'll see copper lower than hydrogen, which means it's less reactive, and it will not replace hydrogen if you kind of looked on that list. And that's one of those ways you can do it. This exact same thing can actually happen with a nonmetal. So if you started with a nonmetal, the only difference is nonmetals will normally make a negative charge. So it will actually come in and kick out the negative guy rather than the positive guy. So it works the same way, except that it started with a nonmetal. It will come in and actually kick out the nonmetal on the other guy. And it will make a new ionic compound here. And that guy that gets kicked out will end up with no charge in this case. So this is a single replacement reaction, only type of reaction where you have like one thing by itself with no charge and an ionic compound, and you'll get somebody getting kicked out if this reaction takes place and some new compounds being formed. Still, again, ultimately what's happening here is electrons being transferred, so ultimately this is still a redox reaction that is occurring. Now, let's talk a little bit about precipitation reaction. A precipitation reaction actually falls under the double displacement category. So this is a double displacement reaction, whereas we talked about at the beginning, there is the only time where you will have two ionic compounds reacting with each other. And always when you have two ionic compounds, as I mentioned before, these guys are just going to kind of switch partners, and you will form your new ionic compounds on the other side. And that is what we see here. We have two ionic compounds. That's a positive negative guy, positive negative. So they're going to switch partners basically. And they're going to hook up and make two new ionic compounds on the other side. And again, just to kind of color code here, the potassium will end up with the nitrate as they switch. And the barium will end up with the chromate as they switch. So again, we're just going to kind of switch partners and make two new ionic compounds. So this is ultimately a double displacement reaction. And one thing that you should understand for a double displacement reaction is this. There is absolutely no transfer of electrons happening here. So this is not a redox reaction. Nobody's losing electrons. Nobody's gaining electrons. We're simply just switching ions, basically. Now, this is called a precipitation reaction because when those ions switch partners, one of the new guys over here will make a solid, which is sometimes referred to as a precipitate. A PPT is sometimes abbreviated for a precipitate, hence why it's called a precipitation reaction. So the broader classification of this type of reaction is a double displacement reaction. A more specific classification is it is a precipitation reaction. Why is that important? It's important because, all right, why that's important is that is one of the three reasons why a reaction takes place, right, is that a solid is formed, and this sort of meets that reaction that we are making a solid in this case. Here's another example of that, or same one. Again, just kind of switching partners, and we always get this double exchange occur. Again, positive, negative, positive, negative. And again, I'm going to make two new ionic compounds on the other side. Yeah. On this type of reaction? On this type of reaction, when you start with two ionic compounds, what will always happen is basically you're just going to switch partners. Everybody switches partners. So when we look at this reaction, the basic two ions that makes up this ionic compound is potassium and chromate. So that's the cation and anion like we talked about with ionic compounds. The two basic guys here is barium and nitrate. And basically what happens is this positive guy, truth be told, they're all just floating around in the solution. They're all freely floating around, all those ions. So when the potassium comes up on the nitrate, they're going to hook up together. And then as the barium's floating around, it's going to start to hook up there with the chromate. The result of the barium chromate hooking up is they will actually come out of solution. They won't float around anymore. They'll come together and drop out as a solid, basically. And so what ultimately is happening is the two positive guys will always switch partners on the other side of the arrow in that case. Uh, so it's going to make two ionic compounds, and just like we talked about with naming, when you put those ions together, it has to equal zero. Yeah. So that's the idea there. So basically, what we have on the right hand side is just those ions coming together properly to make the proper ionic compound. So when we take like the +1 and the -1, we end up with this formula, which is just KNO3, and that's the proper formula you get when you put those two ions together. And when you take this guy, which is +2 and -2, when they come together, you'll get the BaCrO4, one of each. So this is sort of what I was talking about earlier when we were talking about balancing. If you had just, say, the left-hand side, which you probably won't, but if you just had like the left-hand side, what you want to do is just put everybody together properly in sort of their formulas, like their ionic formulas, like you're doing naming. And then what you would do is go like, the K on the left-hand side has like an extra 2. Then you have to go back and balance it with the coefficients in front. And that's why there's a 2 up here in front to balance the actual elements on each side. And that's what you'd want to do is get the right formulas and then balance it. Many people would see this, and if they had to write what's on the other side, many people would go, oh, I see a K2, and I know they switch, so I'm just going to do that deal, right? And that's actually the incorrect formula because that is not how those ions come together because that's K plus and NO3 minus, which means equals 0. Just need one of each. To fix how many we don't have on that side, then we go in front and balance it, and that's the proper way to sort of do that, yeah. Other questions? Yeah. No, so you'll always have in this type of reaction on the left-hand side, you always have two ionic compounds, which basically means on the left-hand side, you'll have two positive guys and two negative ions. And they will always just come together properly on the other side, to make the formula equals 0. It doesn't really matter if your question is, does it matter, for example, if this guy comes first or this guy comes second? It doesn't matter as long as they're on the opposite side of the arrow and as long as they are both the proper formula. Other questions? All right, this type of reaction here is what is referred to as an acid-base reaction. This also falls under the double displacement category. Once again here, we are not having any electrons being transferred in this case. Why is this still a double displacement? Because hydrochloric acid really is a positive and negative guy, and potassium hydroxide is a positive and negative guy. And as always, when you have that combination, that is always a double displacement reaction. And we know that they should switch partners, right? So we should get this deal happening. So what happens when we switch partners here is this. The HCl, the two ions for HCl is H plus and Cl minus. Those are the two things that make up the HCl. The two ions for the potassium hydroxide is K plus and OH minus. So when they switch partners, you end up with something that comes together that is two hydrogens and an oxygen. And we call something with two hydrogens and oxygen, H2O, is water. That is always how water comes. It actually comes from the acid, and the OH comes from the base, as this is an acid, and that is a base in this case. The other thing that forms is this guy and this guy is going to come together, and that's going to make this guy right here. We just need one of each, right? Plus one, minus one. So in this type of reaction, this is actually a reaction of a strong acid, which is HCl, and a strong base, which is KOH. When you make that reaction, you always get two things that are formed. You always get water, and you get what is known as a salt. And a salt is a fancy way, I'm not sure how fancy it is, but it's a fancy way of saying it's an ionic compound, basically. Yeah? So we would call KCl an ionic compound, right? Metal and non-metal together. So a salt is simply just a ionic compound. And you may recognize why this is important, because what did we form on the right-hand side? We formed water. Once again, that is one of the three reasons why a reaction takes place. You will definitely probably not see it, right? Because it'll just look like the solution because it's water-based. You won't actually see the water formed in most cases. But the formation of water is really what the driving force of this reaction is. And once again, there is no electrons being transferred. This is simply just a double switch there of the two positive ions switching partners and making there on the right-hand side. So as we can see here, in the double displacement sort of big category, a more specific way of classifying a double displacement reaction is a precipitation reaction, which means you should make a solid on the right-hand side somewhere. And another way to sort of classify a double displacement reaction is an acid-base reaction. These are also sometimes called an acid-base neutralization reaction. And it's called a neutralization reaction because really the ultimate reaction that's happening here is the H plus from the acid is hooking up with the OH minus from the base to make our good friend water. So that is ultimately what is happening in this reaction. That's why it's sometimes called an acid-base neutralization reaction in this case. The K plus and Cl minus, to be truthfully honest with you, in reality are really not together. They're just floating around the solution. They're what they're called spectator ions. They're just watching everything go on. They're not participating in anything. The two things that are really participating is the H plus from the acid, the OH minus from the base. Those are the participants here in this reaction. Those are the ones coming together to make the water that's actually being formed in this reaction. And that's what the other ions are. In most cases, the salt in this reaction is what are referred to as spectator ions. They're just floating around freely. But we do kind of put them together in terms of the equation. But really, they're floating around freely in the solution. Any questions on that? Yeah. We're going to do it right now. If that's the one you're asking about. Yeah. But I'm assuming it's probably in there as well. Yeah. Yeah. So let's talk about combustion reaction, which actually now is back to a redox reaction. So this would be under the redox sort of category. And most of the time, and probably in your lab manual, in most places, when somebody talks about a combustion reaction, they're usually talking about an organic combustion reaction, which is like when you light your Bunsen burner. The gas comes out, a little spark, a little oxygen, you get some fire. And in a combustion reaction, an organic combustion reaction, which is, I would say, probably 99% of the time what people are referring to when they kind of talk about this reaction, you will have an organic compound like methane, which is usually carbon, hydrogen, or oxygen, plus O2, a little CO2, and water. And that is definitely how you could recognize an organic combustion reaction. If you see O2 on the left-hand side and you see CO2 and water being formed, it is most likely an organic combustion reaction or just being classified as a combustion reaction. As you can see here, this is what happens. CH4, which is our organic guy, O2, CO2, and water, definitely a combustion. all those crazy reactions we balanced earlier, O2, CO2 and water, carbon and hydrogen, combustion reaction. Truth be told, the actual only thing that you need for it to be really classified as a combustion reaction is the presence of O2, really. That's actually the only thing that you actually need, technically speaking, for a reaction to be classified as a combustion reaction. Like I said before, most people will look at examples like we see here with the O2 on the left, CO2 and water on the right, as really the combustion reaction they're asking about. This brings up a really good example of you can sometimes classify the same reaction many different ways depending on what you're looking at. So if I took a reaction like one we saw earlier, which was magnesium plus some oxygen, making a little magnesium oxide, I could definitely look at this reaction and I see two things make one thing, which would tell me this could be a synthesis reaction, right, or a combination. I also see this guy going from 0, 0 to +2, -2, which means we got some electrons being transferred, which means this could be a redox reaction. And dare I say I see an O2 there, which means it could actually be classified as a combustion reaction as well. So you can classify the same reaction in multiple ways depending on what you're looking at. I would say most people would probably classify this reaction as a synthesis reaction, followed by maybe a combustion reaction afterwards, but most would probably look at it as a synthesis reaction. So you definitely could classify reactions in multiple ways depending on what you're looking at. But there really is just these kind of two different classifications of reactions, kind of big umbrellas, which you can then specifically classify reactions more specifically based on what's there. So just to review that one last time, we have the big umbrella of double, and again, that is our general formula of our two ionic compounds switching partners and making new ionic compounds on the other side. And more specifically underneath this is our precipitation classification, where we form a solid, or you could have your acid base reaction, where we form water. Again, no electrons being transferred in any of that situation on the left there. The other big classification, again, is the redox classification, where we have things being oxidized, where it loses electrons, reduced, where it gains electrons. Now, again, more specific classifications of redox reactions is our synthesis, our combination, where again, two things make one thing. We have our decomposition reaction, where one thing makes multiple things or two things. We have our single replacement reaction, where we have a single thing with no charge replacing somebody in an ionic compound and then gaining a charge. And we have our combustion reaction, which again, most people would look at as O2, CO2 plus water, plus an organic guy, or just simply O2 there on the left-hand side. And again, everybody on the right-hand side, although these are more specific ways to classify reactions, they all involve losing and gaining electrons and a transfer of electrons. So all these different reactions and different ways to classify reactions, as we talked about, all boil down to the three reasons we talked about: transferring electrons, making a solid, and making water. Again, those are the three reasons why a reaction would take place. Any questions on any of that there? Okay, so now that we talked about balancing equations, ways to classify equations, let's get into some calculations. And we're going to talk about two types of important, I'll be honest with you, they are really just conversion factors. So molar mass and Avogadro's number are really just some important conversion factors that allow us to convert from one unit to the next. And we'll talk about where we get these numbers from in just a second. Let's start with molar mass. Actually, not. Let's start with the mole. And the mole is a word that is used in chemistry to describe a certain amount of something. Just like in life, we have some words that we use that represent a certain number. If you say you have a pair of shoes, most people know you're talking about you got 2 shoes, right? You got a dozen roses. Hopefully that came with 12, right? Unless you got the baker's dozen, that's 13. If you got a gross of pencils, or you can still find somebody that gives out pencils, that's 144. That represents. So in chemistry, we have the word mole. And just so we're clear, one thing that's confused by a lot of people when they see mole, they did have to come up with an abbreviation. So they didn't have a lot of letters to work with. So the abbreviation for mole is MOL. So if you see MOL, that is moles. It is not molecules. People, for some reason, when they see MOL written, they always kind of jump right into molecules. That is the abbreviation for moles. I will say probably in chemistry, if they are talking about molecules, they will write out the word molecules. Yeah, so they'll just write out the whole word molecules. And again, if you see MOL, it is moles. The moles represent as many elementary units of atoms, molecules, as there are in exactly 12 grams of the carbon-12 isotope. You might remember that the carbon-12 isotope is the isotope that was used to figure out the atomic mass that we see on the periodic tables. That is the guy that has 12 AMU. Now, I'll come back to those pictures, I think. When we talk about a mole, it does represent an actual number, and that number is known as Avogadro's number. And Avogadro's number is 1 mole of anything is basically 6.022 times 10 to the 23. So we do use this sort of rounded version of the number here. Now, when we're using Avogadro's number, the units that go with Avogadro's number can change. They can really be any units you want. They could be units of atoms in some cases. They could be units of molecules in some cases. They could be particles in some cases. They could be pizzas in some cases. They could be shoes in some cases. Except for the occasional pizza problem, you might most likely see atoms and molecules here in this class as the units that are associated with it. And what do we do with this thing? Well, this thing really is and should be thought of as just a conversion factor. So like any equality, you could write 2 conversion factors for this. You could write that 1 mole of anything has 6.022 times 10 to the 23 atoms. Or you could flip it around and write 6.022 times 10 to the 23 atoms has 1 mole. So we use this as a conversion factor, like in dimensional analysis. And the conversion that we are doing here is between moles and atoms, or it could be molecules as well. Again, it could be either one. And again, going backwards. Now, sometimes people want to use Avogadro's number in all calculations, and that's a really bad idea. So you should really only use Avogadro's number in situations where the problem either gives you a number that's in atoms or in molecules, or it asks you to solve for something in atoms or molecules. If there is no mention of atoms or molecules, you probably should leave Avogadro's number on the side there, yeah, and not use it. Now, you could take anybody off the periodic table, like hydrogen, and you could say in 1 mole of hydrogen, there is 6.022 times 10 to the 23 atoms of hydrogen. You could take carbon off the periodic table. And you could say in 1 mole of carbon, there is 6.022 times 10 to the 23 atoms of carbon. And obviously, for each of those, you could write 2 conversion factors if you need to use it in a conversion problem. You also could go, if you had water, for example, in 1 mole of water, there would be how many molecules of water? 6.022 times 10 to the 23. We use the units here of molecules because water is a molecule. It is not an element by itself or an atom. So we use the units of molecules here with Avogadro's number rather than atoms. If you had CH4, 1 mole of CH4 would be 6.022 times 10 to the 23 molecules of CH4. So again, each of these are going to be used as a conversion factor to convert again between moles and atoms. So if you have if you have if you have moles and you want atoms or molecules, you need to multiply by Avogadro's number. Again, dimensional analysis, opposites cancel, right? Multiply the top, divide the bottom, moles cancel. You're left with atoms, or you could do that in molecules as well. If you are starting with atoms or molecules, you need to divide by Avogadro's number. Put it in the opposite location. Again, multiply and divide. Atoms will cancel, going to leave you moles. So again, that is mathematically how you would use Avogadro's number. And again, it should mention something about atoms or molecules in that problem for you to use it. Any questions on that there? And again, you could use that for anything. And whenever anybody says a mole of something, the number that's associated with that is that Avogadro's number. Let's talk here to finish up on the very probably most important conversion that you will get, and that is molar mass. The units of molar mass are grams per mole. It is really the conversion that we use to go between really 2 important conversion factors, and that is if you have grams and you want to get to moles, or you have moles and you want to get to grams, it is the molar mass that we use to do that. Where do we find the molar mass? We find it right there on the periodic table. So the molar mass is found on the periodic table. If you look up hydrogen there, it is that number on the bottom. Now you might remember that that number on the bottom was the atomic mass in AMU. But oddly enough, through conversions, the atomic mass is the exact same number as the molar mass. And the reason we usually take the number off the periodic table as the molar mass is because it has units of grams per mole. And if you went to the balance and you weighed something, they typically don't give it to you in AMU, they give it to you in grams. So grams is a more useful unit for us. So if you went there and found hydrogen, hydrogen's molar mass would be 1.008 grams per mole. The number always stays with the grams part, and it's always per 1 mole. You could think of this as a conversion factor, 1.008 grams over a mole of hydrogen, or a mole of hydrogen, 1.008 grams. You could do that for carbon, 12.01. Carbon's molar mass would be 12.01 grams per mole. Again, you could use it as 2 conversion factors, 12.01 grams per mole of carbon, or a mole of carbon, 12.01 grams. You could also do this for something that is not just an element by itself, like our friend water. What you would do is you would go to the periodic table and add up all of the parts of it. So there are two hydrogens. Each from the periodic table is 1.008 grams per mole. That represents the hydrogens in this formula. And there's an oxygen, which is 16 grams per mole. That represents the oxygen. If you add that together, you get 18.02 grams per mole. That is the molar mass of water. And again, you can use that as a conversion factor. So if you have some type of molecule or compound, you basically go to the periodic table, add up all the parts, and that will give you how many grams there are per mole. How does this all relate together? If you have 1 mole of hydrogen, that would equal 6.022 times 10 to the 23 atoms of hydrogen, which would represent in grams 1.008 grams. Yeah, so they're all equal to each other. Yeah. Same thing with the water. If you had 1 mole of water, that would have 6.022 times 10 to the 23 molecules of water, and that would represent 18.02 grams of water. If somebody said, hey, I have 1 mole of water, how many grams is that? 18.02 grams. How many molecules of water would that be? 6.022 times 10 to the 23. So out of both of these conversion factors, this is the one that you will use the most in chemistry, which is the molar mass. Again, basically achieved from the periodic table as to where you can find that conversion factor. Any questions on that there? Yeah. So when we're doing molar mass, it's a couple important things. You should do it based on the formula. So in the formula, there's only 1 oxygen here, if that's the one you're talking about. And for hydrogen, there's 2. From the periodic table, that is what is on there, which is for the oxygen. We did. That's what this is right here, times 2. Yeah. So yeah, 2 times. Yeah. Other questions?